Um, that way we can all see it, and it also helps me read your facial expressions to kind of see, is it confusing you, or otherwise. Oh, there's a chat. All right, Suleiman's giving me the solves a whiteboard problem. I tell you what, Suleiman, I will get started, and then and so there'll be a couple breaks here when you guys are supposed to work through things. While you guys are doing that, I'll read the link you gave me, and maybe I can fix it. Okay. All right. So I will try to be on that as we do all this. I I have to say, it's kind of like having all new people in my class because I've never seen you guys without a mask. So, uh, oh, Suleiman. All right. Now I recognize him. So there you go. There you go. Okay. Right. So you guys should be able to see Notability, which is my note taking app, but it should be the screen. Is that okay? Can you see that? All right. Good. If at any point, just call out um, if there's a problem. So this section is on forces, which at least the first day is usually very intuitive. So I think there's a good chance we can get through two um, activities. Well, I'm going to try. I don't know if we can or not, but I'd like to. Um, so the first thing, which is to be clear about, is what is a force? A force is any sort of a push or a pull, right? So when you push something or you pull something, you're interacting with forces. Okay, it's really that simple. Um, as far as the as physics is concerned, it really doesn't matter. If I take my finger, I can the effect of pulling it one way or pushing it from behind. I can either pull it from the forward direction or pushing it from behind. It doesn't matter. I have a prop, I might as well use it. All right. So it really is the same motion or has the same effect whether I push this or I pull it from the other direction. It has the same effect. So pushes and pulls are forces, no difference. We don't really, in physics, nature doesn't seem to care about whether we call it a push or a pull. All right, so that's what they are. And what we're going to try to do is understand this. We're going to have an interaction, describing interactions using forces, and understand their effects on the motions of things. All right, so that's the main thing here. All right, so initial ideas. The first thing they want us to do is to imagine there's a soccer player kicking a stationary ball, and oh, before I get into this too far, just I don't know if you saw in the announcement, I linked a scan for activities 1 and 2 to the Blackboard page. So if you don't have it, you can download it there if you needed it. So, anyways, all right. So, all right. So they want you to remember what happens when you have a soccer player kicking a stationary ball, and as he interacts with it, he kicks it. It starts to move, and after the kick, the ball rolls across the grass and eventually comes to a halt. And they want you to sketch a speed versus time graph for that motion. So it starts at rest, it's initially stationary. Okay, so kind of if I highlight key words here, um, it starts out stationary and sorry, that's not, there you go. It's stationary, and then it starts to move, and then it rolls across the grass and gradually comes to a halt. So try to sketch the speed versus time graph. This is something we did months ago. Just they're wanting you to remember that. Okay, so if you can sketch it on paper and then hold up a picture of your artwork. Okay, good. Oh, yeah. 1. Okay. Julie, I can't see. All right, I think it's right. Yeah. Okay. So let's think about that. So it would start out and it would be 0 speed. Let's say it was, I mean, mine might be drawn a little differently than yours, but let's say no speed, no speed, no speed, no speed. Then we have a kick. And so the speed quickly increases. And then as it goes down, it would just sort of slowly decrease in speed down to 0, say. And we know it has to reach 0 because they say it comes to a halt. Okay. So even if I didn't comment on, maybe I couldn't see your artwork, did you have something kind of like that? You know, maybe it was rounded. That'd be okay. You know, maybe this was rounded. That's okay too. I'm not worried about that. But the idea that it would start at 0, jump up and jump, and then just kind of slowly approach that. All right. So hopefully you've got something like that. Go ahead with your pencil and indicate when you think the foot was in contact with the ball. I will do the same here.
Hey Sean, could you see I typed there like earlier?
The whiteboard comment?
Yeah,
Yeah, I said I'm going to give you.
like
There are going to be some moments here where you guys have to. Here in a bit, we're going to play a video, and then I thought
okay,
I would read through the blog you sent when I was doing that, and then
okay.
if I can get it to work, then we'll do it that way.
Mhm.
Okay. I just didn't want to. I didn't want to follow the link and you guys just stare at me reading the thing for 5 minutes. So I thought we'd start, and then while you guys are working, I'll try to figure it out. Okay. Um, okay. So in your artwork or in your graph, um, can somebody call out when you think the foot was in contact with the ball
On the upward motion.
on the upward motion? Does everyone agree with that? Yeah, I do too. So if I was going to do that, I've changed my color here to green. I'd kind of, this is when the foot was in contact with the ball. So remember, it's the entire time the speed was changing, and it's increasing because the foot made it increase. Okay, awesome. Um, yeah. All right. So then it says indicate during the period where you think there was a force pushing the ball forward on the graph. So take a second and think about that. When do you think there was a forward force? Remember, a force is a push or a pull. A push or a pull. If we're talking about a forward force, we're probably thinking about a push. But right. Okay,
Wouldn't it be during the same time that you're kicking it?
you got it. Yeah, so I'll do that in blue. Okay. I'm not going to try to pull any punches here. If you're noting that they are occurring at the exact same times, that's how it works. Okay. So when there was contact is when there was the force, right? No surprise. If you've ever watched little kids play soccer, sometimes they miss the ball and the ball doesn't even notice them, right? They swing their foot, they miss, there's no contact, and the ball keeps on going. It doesn't even react to them. So you have to have contact. Well, not for this kind of a force, like a kick. You need contact. Okay. All right. So why do you think the ball gradually slows down and eventually stops after it's been kicked? Somebody else. What do you think? So why do you think it slows down and eventually stops?
Because of the friction.
Because of the friction. Yeah. So, um, hmm. All right. So, yeah. So that's a great answer. And then they want you to draw two pictures of the ball, and we're going to use arrows to show what forces, if any, you think are acting on the ball at two different times during the motion. So I'll do the first one. Okay. So, well, okay. What are the two forces we think are at play? Well, okay. So there's some sort of a kick kind of force, something coming from the player. And what's another force that might be at play? Might be significant here. Suleiman just said the word.
Friction.
Friction. Yeah. Friction, it exerts a push or a pull, right? You can use friction to yank on things if you like. Okay. Oh, Christmas is or Thanksgiving's done. Okay. Over the winter break, just to test this, you're sitting at the kitchen table. You got a tablecloth under the dishes and the plates, and you yank the tablecloth out of the way. The friction between the plates is going to pull them off the table with the tablecloth. Okay, that friction is exerting a pull in that case. So good. Okay, so what they're after here is
We don't have to implement that gravity interferes with the friction or the weight of the ball or any of that.
okay. All right. So right now, okay. So let's talk about that. The real world has many forces all happening kind of all at once, right? And so with a lot of these situations, they're kind of wanting you to zero in on the most important one in each scenario. So in this case, gravity turns out is a force and it always points down towards the surface of the earth. And then there's some sort of a normal, well, we call it a normal force, some sort of force pushing up from the ground to keep us from like tunneling, like sinking into the earth. Okay. But they're wanting us to focus. So those forces are there, but they want us to focus on the side to side things because as we'll talk about later, right? When the ball is moving along the surface of the earth, gravity and that force from the earth are kind of canceling each other out so that they're there, but they zero out. And so they aren't necessary to describe the motion that we're seeing. That's what I will say. So,
Okay, so we're going to focus on friction.
well, and the kick. The side we're
Right.
focusing on the side to side, the horizontal forces. Yeah.
I'm just making a note of it. That's all.
Yep. Yep. No, and you're right. Real situations have, a lot going on. So you kind of have to unwind them and identify what's the most important one in each situation and then kind of go from there. And sometimes there are many that are important. Good. All right. So they break it down and they want you to identify the ball. And this is going to be common. When we have forces, we indicate that with an arrow. So during the time when the foot was in contact with the ball. So here's a ball. And then we're going to put an arrow representing the force. Now, the book is kind of goofy. Sometimes, well, at least the previous edition, I think this one will too. Sometimes they make a difference between an arrow with two sides that they use for forces and an arrow with one side. They'll use that for speed. I think that's too confusing. Instead, just write force. You can just use F and I'll write F with a subscript kick. All right, just so you know what it is. And then if we want a speed, an arrow for speed, or then we'll just write speed. All right, and then it's just clear. So there's no ambiguity. It's all obvious. Okay. I kind of jumped again, but that's all right. Label your arrows to show where you think the force comes from. Well, I would always label it as an F for force, so we don't confuse it with anything else. and then I put kick. So you know where it comes from. All right. Very good. And then if we wanted to think about it, well, we'll just leave it there right now. All right, what about after the foot has lost contact with the ball? Oh, incidentally, coming back to Julie's point with other forces, in real life, in reality, there's also friction in this first moment, but it turns out that the friction is just tiny compared to the kick, and so we will ignore it. In that startup part, when it just gets going, there would be a little friction arrow, but we won't worry about it. After the ball is moving, okay, so the ball, this was at the beginning when the initial speed was 0. Now the ball is moving. So let's go ahead and say that it has a speed. I know they don't quite say to do this. Let's just say that the speed, it's going forward. And what is the effect of friction going to be? Which way do you think friction is going to act on
The
it?
opposite.
The opposite, yeah. Okay, so, and again, I don't care if you think of it as a pull or a push, but friction is going to act the other way. And typically, I would expect the friction force to be smaller than the kick force. So I would draw it with a smaller arrow. And I would write force, friction. I apologize. My handwriting is always bad, but it's especially bad with a stylus. It just seems to get worse and worse. Okay. So when they talk about a force diagram, this is the kind of thing they mean. You draw the object, and then you draw an arrow representing all of the relevant forces. And you have to read the scenario to decide what are the relevant forces. There could be other things like gravity and force coming from the earth, but those aren't going to be relevant for this motion. So that's why we're just ignoring it. Okay? Are there any questions on that? All right. I know we would have been doing this all. You guys, it's more me talking than in class, I think, but that's just probably how it's going to be. Okay. So the first experiment is here. You guys are all supposed to get your low friction carts out. No, it's not going to work. And then a force sensor. I'll show you. We have these. You guys have already seen the motion detectors. There are also these force detectors, and what they do is they just have a hook and they go into the computer just the same. And if you pull it away from the box, it calls that a positive force. If you compress it, it calls it a negative force. And you can just think of it as like a scale, like a bathroom scale, essentially. It has a hook, and it reads out to the computer. Okay, so I made some videos doing the activities over the weekend, and so that's how I'm getting the results. So it's really just this simple. Okay, so sorry. Ugh. Okay, so do you remember the situation where we had a cart that was going down the track and we tapped it several times, and then how the speed would kind of, it'd be going and then it would go up, like, and then up a little bit more, and like a stair step sort of thing. That's what they're trying to remind you of here. And this is when you're giving it gentle pushes. Let me highlight the keywords here. Gentle pushes or pull in the same direction as the first push. So in the same direction of the motion. All right. One of the later activities reverses it all. So right now the key things are a push along the motion, one direction. We're doing things along a line. We're not doing things that move in like a roller coaster. And the push is in the same direction as the motion. And that's what we did. And this is the graph. Hopefully you guys kind of remember that. What you're seeing here is a big spike from the push, a little bit of a decrease because of friction, a big spike because of a push, a little decrease because of friction, and so on, right? Can you guys give me a thumbs up? You remember doing that way back, I don't know, forever ago. All right, awesome. Okay. Oh, I just gave you the answer. You're supposed to color in. All right. Color in when you think the hand was in contact with the cart. This first activity is just kind of, it's really just too easy. You kind of guess all the answers, right? So it's just like before. These are when we had contact with the cart in green. Why? Well, because we did the lab before and because your idiot instructor told you the answer. But really, hopefully it's because we saw that before from the previous activities. All right. So now they want you to do the same thing. Basically, instead of talking about your hand pushing and interacting with energy like we did before, and chemical potential energy and all that, and kinetic energy, they want you to describe this and analyze this using the concept of a force. So use a colored pencil to indicate, wait a minute, is that the same one twice? Awesome. I just losing my mind. There you go. There you go. I knew this was coming up next. They want you to indicate when you think a force was applied to the cart. So what do you think the force versus time graph would look like to correspond to this motion? Remember, the hand was in contact during these intervals. So take a second and draw when you think the hand, or sorry, what you think the force versus time graph would look like. Okay, and when you have that, hold up your artwork. Okay, I just got one. Does anybody else have something? Okay. Anybody else want to show their artwork? All right, so Julie's got one. All right, so let's do the experiment and see what we get. AKA, let me switch the video. Maybe if I can ever get this thing up. There we go. Thought I lost it. Come on. Sorry, I'm fighting with Zoom here. Physics. And I think it's this one. Sorry. Trying to, yeah, all right, that's what I want to do. Zoom share video. Lost my, doing this on my laptop. I've got too many things going. There we go. Now, can you see that? It should be black screen right now. You see that? All right.
Hey,
I'm going to show you my homemade version of the experiment you guys did, sorry, months ago when we were talking about energy ideas. So my assistant will go ahead and hit start. Okay, go ahead. Stop. If we were to look at the speed versus time graph, you'll notice same thing we saw before. Whenever there was an interaction with the cart, between my hand and the cart, the speed changed. So speed, wherever there's, so there's a change in speed here, that's when my hand interacted with it. It's change in speed, so there was an interaction with my finger. Change in speed, interaction with my finger. And this is when I brought it to a stop here at the very end. Okay. All right, so what did we, all right, so that's the change in speed. I don't think that was the video I wanted. I'm gonna do the other file. So that one that was the one where you're pushing with your hand. I think I want, show this one. Can you guys see that? Can you see this video? The should be 2 graphs. Can you see the video with 2 graphs? No. All right. Try that again. Now can you see 2 graphs? Awesome. A similar kind of experiment, but this time I have included a force probe. So this is a device which measures forces, pushes or pulls. And what we want to do is see what is the connection between the forces acting on the cart and the motion of the cart. So let's follow it. Now I have to be careful because the cord wants to drag. And hit start. Pin. Okay. Now let's change the scale here and go to what I want you to do, and I'm just changing it so it's more visible here. It's a little tough, this sort of homemade setup. What I want you to see is that down here are the times that I pulled with my hand on the force probe or on the cart. And notice the connection between when I pulled with the force probe and when the speed changed. I just want to make a comment. It says acceleration, but it's measuring force. Okay, so this is the force. This is when there was a force. All right, so just want to make that comment right there. I know the graph says acceleration, but it's force. Okay. Here, when I pulled with the force probe, the speed changed. Finally, same over here. Right. So notice that whenever there was a change in speed, there was also a force acting on the cart. Okay, so that's kind of the point. Let's go back to ability. All right, so the force versus time graph, I know it said acceleration, but the force versus time graph is actually a little different than what you guys were indicating. Basically, the force versus time graph would, if there's no contact with your hand, then there will be no force. So you can only have a force when your hand is touching the cart, and in particular, it's when the cart speed is increasing. So it would have looked like this. It'd be, draw this in blue. It would be 0 till about here because there's no contact. And then maybe I'll kind of draw these in, I'll connect these up here. And this would be in blue. And then when the hand was touching, you could have a force during this interval, and then no contact. So put that in blue. And so if there's no contact, there can be no force. And then contact. So there would be a force. Oh, sorry. And then there's no contact with the hand here. So there can be no force from the hand here. And then you have a push, so you get something like that. And then no contact, no contact. All right. So I think pretty much all the graphs you guys showed me were kind of like stair steps for the force versus time graph. But you have to remember that when the hand loses contact with the cart, that there can't be any more force. So it has to go to 0. So whenever there's no, when it's not touching the hand, the force has to be 0. There we go. Does that make sense? Are there any questions on that? So here's kind of the tricky thing then. The cart's moving and it has energy, as it moves, and it carries that energy with it. When you look at the force graph that I just sketched, does it seem to have force and carry the force with it? No, the force is there, then it's not. And then it's there, then it's not. Then it's there, then it's not. Force is different than energy. Energy is something you kind of have, and you can give it away or get some more, but you carry it with you as you wander around. Force isn't something you carry. You can't put it in your pocket. So it's not like Star Wars where they say, may the force be with you, as if you own it or you carry it with you. I don't know. It's not like that. Its forces have to do with interactions between things. So that means as objects move around, if they stop interacting, the force goes away. It's just that simple. I mean, it's really, so it's a little, it's connected to energy ideas. They are related, but they're not the same. Right? And so, and when if you read things or you hear things on the news, people equivocate and they kind of talk about forces sometimes as if they're energy and vice versa, talk about energy as if it's a force. And the language is wrong. I'll give you an example of it that comes up. When people talk about electricity, have you ever heard anybody talk about EMFs? Do you know what EMF stands for?
Electromagnetic fields.
Actually, in a circuit, it's electromotive force is actually what it means. They called it a force. In reality, it is much closer to an energy concept. So, historically, they weren't sure what was going on, and so they chose vocabulary. Turns out they chose wrong, but it took hundreds of years to figure that out. So the vocab is important, and the way that you talk about it is important. An EMF is more associated with a voltage, which is closer to an energy than it is to force. All right. Okay, they have a movie. We can do the movie. The movie is just going to show exactly what we did, where whenever you have a force, that's when the speed can change. Okay. So let's turn that around. If you were to look at a graph of speed versus time, and you saw something like this, if I ask for you to immediately tell me when there was a force versus time. Now, Suleiman, while you guys were doing that, and while I showed you the first, that's why I showed the first wrong video, because I wasn't paying attention. I was reading the page and watching the video that he sent me. All right, he tells me, if I go to share and disable, no, I don't want that. Enable annotate. All right, so what I want somebody to do, somebody who's really brave, Haley, what I want you to do is try to draw on my picture. And first of all, mark on my speed versus time graph when my hand was, when a hand or something was in contact with the object. Can you try to do that with your finger? See if it'll work. Will it let you annotate?
There
No.
should, when you click view options, there's annotate. And if you click annotate, you can actually draw.
View options.
Wait. Go on where again?
Oh, I know why this won't work. Duh, I'm an idiot. Because I'm
Yeah.
doing this in my own
Can you see
program.
this?
It's not in a, mine is not in a whiteboard. Oh, there I can see yours. Perfect. Yeah.
Yeah.
Can everyone see what he wrote? Okay, so
Yeah.
you guys,
But I
guys,
don't-
It's on the top of the screen. There's view options. Do
Okay.
you see?
Oh yeah, I see it.
Did you click it? There's annotate.
okay.
Oh,
Okay.
wait
It's
a
there.
minute. Oh.
Yes.
Wait, how do I get rid of it?
Oh, Henry wants
They
to
should be
control my
clear.
screen.
Clear.
Clear.
All right. So
Oh,
there are
okay.
two things. One is to just draw kind of inside zoom, and the other option is to actual. So I'm using a different program to draw. I'm not using Zoom. I'm using Notability, which is a note-taking app, and the other one is to request access to do that. Either one would work, but if you draw, I think it's easier than everybody can. I think that's better. All right, now Haley, on that diagram right here, can you sketch in when someone could be touching the object?
Can I just put a little dot? Or I don't know. I'll
I've
like
never done
write.
that before.
Oh man.
It's okay. We're just judging. We're just judging and
Okay, right there. Is that where?
during the slope.
Yeah.
Good job.
Yeah.
All right. So then drop that down on the force diagram. Indicate where you think there could be a force applied to the same object.
You want me to do it?
Yep.
Okay. Do you want me? Okay, I'll just
So
go
just
for
draw
it.
where it's 0 and draw where it's not 0, like I did before.
Okay. So it's gonna go there. Oops.
It doesn't have to. Be.
And then I cannot draw with my finger.
Okay.
And then something like that.
That's the idea. That's right.
But
Right. Yep. That's exactly right. So so there's nothing when there's no contact. Something there. So notice then, we would have said that an increase in speed indicated a gain in kinetic energy, some sort of an energy or mechanical interaction from an energy point of view. Now we're going to interpret a change in speed as some sort of a force was exerted on it. Okay, and they're wanting you to get the connection between forces don't, so you can have a speed here, there's no force over here. You can have a speed with no force. Forces don't cause speed, forces cause changes in speed. Okay, let me emphasize, that's really important. Forces cause changes in speed, not speed itself. Okay. Remember when we had the hovercraft and we said that if you could kind of isolate something and once you started it moving, it would just go and go and go forever. Remember doing that? We did that in the hallway, I think, right? And we said it would just go forever until it ran into something. Okay. So what that means is, if it doesn't run into anything, it has a speed. And if it doesn't run into anything, there's no force. So you can have a speed without a force. Forces don't cause speed. Forces cause changes in speed. That's really important. It's a tricky thing that, oh, I see. All right, Haley, I think you got to delete your thing. There you go. All right. Okay. Very good. So 3 students are discussing the motion of the cart and the force acting on it, blah, blah, blah. They all agree that while the hand is pushing, there's a force being applied to the cart, but they have different ideas about what happens during the periods when the hand is not in contact. So what I want you to do is in the chat window, indicate who you agree with or none. You can write that too. Getting a lot of votes for Amara, but not everybody's voting. Some people are. All right, Henry, sure. Just copy everybody else. Okay, so let's go through them in turn. You guys, I agree. I think Amara is on the right idea. So, what is Samantha? She says force, but what is she really thinking about? What's she really talking about there?
Would it be energy?
Yeah, she's.
Oh, sorry.
It's fine. It's fine. No, that happens with Zoom. It's fine. It's better that everybody participates all at once than nobody participates. All right. Yeah, she's thinking about energy. And she's using force language, but she's thinking about energy because she's talking about something being transferred and carried around. Yeah. So that's Samantha's not on the right track there. Victor is saying she thinks the force stops when contact is lost. That sounds good. But some other force must be taking over to keep the cart moving. Well, so he's going back to this idea that you need to have a force in order to have speed, that force causes speed. That's not right. Force causes changes in speed. You can have a speed with no force. Right? We saw that when I can't remember who we pushed down the hallway in on the hovercraft, but you can have a speed without a force. You just can't have changes in speed without forces. And then Amara is on to the right track there. Okay. All right. Now, I'm a little puzzled because my file doesn't have, did I not scan it? I'm sorry, I fouled up my, okay. All right. So, apparently I did not scan in the summarizing questions, so I will upload those and add that. I would like for you to do those. They're not hard. They're just really just no harder than what we're doing. Okay. All right. So I want you to go through those on your own and then upload those. I think I have the due date set for Wednesday, but you know what? I'm going to push it back to Thursday. That way, because this is all a little different. So if you were to get stuck or confused, you could ask when we meet on Thursday. All right. So take a look at it though, please, and try to. If you get it done early, then it's just easier. All right. Other questions on that? So the key ideas are. You only if there's no contact or well, when we talk about pushes or pulls with a hand anyway, well, how to say this? Sorry, the key ideas would be the indication of a force is a change in the speed. That's a key idea number one. And really important idea then is that you don't carry the force with you. It's only during the change in speed that the force is present. So forces can come and go. It's not conserved. Remember, with energy, we had energy conservation where you had energy and you kind of carried it around. And the changes had to add up to whatever came in, accounted for changes on the inside or whatever energy left, inputs and outputs, that kind of stuff. Forces aren't going to be like that because they don't add up. They can come and go. Whenever there's an interaction, there can be a force. In general, there will be one. And when there's no interaction, there's no force. It comes and goes. All right. Questions on that? All right. So I'm going to roll into the next activity. Please do the summarizing questions for activity one. They're pretty easy. The first activities are always super easy. Okay. Can you guys still see the can you see activity two there? Okay. All right. So they're kind of just having you replay all the little activities and hands-on things that we did with energy ideas. So we pushed one time, then we tapped it many times, and then we did one long steady push, that kind of thing. So that's what we're going to do now. We're going to describe a long steady push on the cart from a force point of view. Okay. So so the key ideas here, keywords are going to be a constant strength push applied continuously. So we're not talking about, push, pull, push, pull, push, pull, something variable like that. This is just steady, constant force. What you can imagine, and this is actually one where it is really good to do it in person. The idea is if you can imagine pushing the cart with your finger and, I gotta go the other way. The camera goes reversed. All right. With your finger, push it and imagine what it would be like if you kind of made the pressure on your finger feel constant. You're not keeping the speed constant necessarily, you're keeping the pressure constant. That would be a constant force coming from your finger. That's kind of the idea. All right. So I want you to imagine that you had a cart like this, and imagine you push it in the direction of motion with a constant, steady strength push. What do you think the motion of the cart would be like while it was moving with the push? Okay, think about what you think. Maybe think about that speed versus time graph. What do you think would happen? Because that's what they want you to do. So sketch your speed versus time graph, and then I'll have somebody. I'll have a special victim. You could assume, if you want to, assume it started from rest, and then you apply a constant strength force just the whole time. All right. Give me a thumbs up if you've got a sketch of what you think it might look like. Nobody? Can you give me a thumbs up if you think you've got a graph? No? Nobody? All right. Well, let's think about it. If there's a push, a constant push, what does so constant force, what's the symptom or what's the clue when you look at a speed versus time graph? What would tell you that there's a force?
Change in speed.
Change in speed. And if you just steadily apply a force, then what kind of change in speed would you expect it to have? Would it just be a one-time thing or something else?
A constant increase.
Yeah, just a steady increase in speed. Okay, so think about that. So, it might start from here, and then you apply a steady force, is you're going to have a steady increase. Oh, still applying same force. Steady increase. Oh, still applying same force. Steady, steady, steady. Okay. So you would if you just keep applying a steady force, you would just expect a steady change in speed, for every interval. That would be my prediction. Okay. Just for fun, over here, if we were to sketch a force versus time graph to correspond to this motion, what would that look like? Let's see. Who hasn't? Tanisha, can you modify mine? Can you sketch in what you think it would look like in the force versus time graph that would correspond to this motion? Maybe it won't go. Yeah. Are you able to do it, or is it not going for you? Not going. All right. Well, let's try to figure that out. So let's go. We click on. So I go to Zoom. Mine looks weird, different because it's.
Is it going to be the same thing? Because we are giving force.
Well, okay. So is your force changing in this situation? No. So it'd be.
A horizontal line.
Yeah, that's right. Each moment, if you were to kind of sample it, it's just going to be the same. So it's just going to be a horizontal line. Okay. Yeah. So that's what we would expect for a force versus time graph. Okay. So what they have next is, so we're going to do a force versus time, and they're going to have you they're going to have a fan. My son and I made these videos. So the idea is you put the fan, here in a minute, we're going to do this in the video, but you put the fan on the backside of the cart. It's kind of like those boats they have in the swamp, like in the Everglades, where the fan propels the boat. Have you guys seen those? It's like, all right. So that's the idea, and it goes down the track. All right. So So I guess the very first thing is trying to do it with your finger. And it just turns out it's really hard to do that with your finger. Um, what happens is if you just try to push the cart, if you don't maintain, it's easy for you. It's like the cart kind of runs off away from your hand. You have to, it loses contact with your hand. So it's tricky to keep a constant pressure. So that one, I'll have to kind of tell you the answer. And then if I tell you the answer, you can kind of see it, but it's also a little bit iffy. But then when we use the fan, that gives a nice steady force and you can really see it. Okay, so I'm going to show that movie and I will share that with you. This one, make sure it's the right one. Oh. All right, yeah. So you have to watch the little screen in the to see the. So the cart will be visible in the cart will be visible in the little window. In this video, I'm going to attempt to pull the cart with a constant force. Now, I may not be able to do it with my hand, so we'll see what happens here. Okay, can you push start then? My helpers, hold on here, and all right, I'm going to try to pull. Okay, very good. That's not bad. You can tell here where there were dips and things, I started to lose contact with the cart. I couldn't maintain that. And then at this point here where it's crazy, that's where who knows what happened. Probably the detector saw the wrong thing. Okay, so take a second and think about what is happening to the speed over the time when I was able to continually apply a force, a steady force. That's important. Okay. In this video, I'm going to attempt to pull the cart with a constant force. Now, I may not be able to do it. There, sorry. Sorry. Oh, come on. Can you guys see my notes here? Back? Okay, good. So what happened there was I was pulling on it, and then if you go back to this prediction here, it goes faster. If I apply a steady force, the force is constant, but the speed gets faster and faster and faster. And then what happens is my hand has to go faster and faster and faster to keep up with the cart. And then I kind of lost contact. It just wasn't. I wasn't able to make it super steady. So, but that's the idea. So, all right. So how does it behave as we push it? Well, I would say the speed increases steadily. And how easy did it seem to maintain a continuous constant strength push? I'd say not very. Whoa, can't spell. Right? I lost it after, I don't know, 2 feet. Right? So eventually it gets, and it just gets harder and harder and harder, in reality. Have you, who has a sibling? Okay. I guess a younger sibling in particular. All right. So do you know if you have a merry-go-round or you try to push it and you're trying to cause the speed to go faster and faster and faster, right? You want to go faster, faster, faster. And what happens eventually? You can't run fast enough to push it anymore. It outruns you, it feels like. You can't, it's hard to keep pushing it with that same amount of effort. And that's what happened to my finger. It just the cart outran my finger, and I wasn't able to do that. Okay. Their videos just like mine. So it kind of increases, but with various wiggles. So yeah.
All right, so it asks, why do you think so? Why do you think that is? Is it because it depends on what you're pushing, right? The lack of friction, or if it has wheels, it makes a big
Use
difference whether you
our
can keep up with it.
ideas. How about this? Use our ideas of energy to answer that. So if the cart's going faster and faster and faster, what does that mean in terms of its energy?
The kinetic energy is increasing.
Where did that kinetic energy come from?
Loss of CPE.
And I didn't eat enough breakfast. Eventually I just run out. My muscles, that's literally what's happening, is there's just a limit to how much my body is able to deliver energy, the rate at which I can deliver energy. And at some point the cart gets going so fast, I cannot, in order to increase the speed would require more energy than I can supply. So I just can't. I think that's the best answer. And that's kind of indicates a little bit of how that there is a connection between the energy ideas and force ideas that we're talking about. Yep. Okay. All right. And their graph is really the same as mine. We can watch the video, but it's literally the same idea. They're doing this exact same thing I just did. Okay. You know, there's just a limit to how fast I can move my hand, you know, a certain number of miles an hour. And so that I won't be able to do better than that. Okay. Next up, it's really the same experiment. It's just going to be done with a cart with a fan unit attached to it. Okay, so you're going to attach the fan to the cart. And the benefit of that is that, you know, batteries provide a more or less constant voltage. It turns out that's going to, in this situation, means they're able to more or less generate a constant force in the situation. I know voltage isn't force, but it turns out it works out the same way. So the force that the fan is able to deliver to the cart is pretty much constant. And so it's just going to replay the same experiment, but instead of using my finger to power it, it's just going to be the fan powering it, and it'll be a better graph. Okay, so let me try to get that going, maybe. And maybe, okay, so I'll share that. Hello. In this video, I needed an extra pair of hands, so I have an assistant, Finn. Hello. And he's going to help me turn things on. So last time, I tried to push the cart with a steady force with my finger, and it was really tough to do. So what I have here is a fan, which is going to blow steadily, and so therefore it's going to generate a more or less continuous, constant, steady force on the cart. Okay, so Finn, when I say go, please turn the fan on. Ready? Set. Go. Okay, that's better. Notice it's kind of similar. Let's talk about what happened here. this point, nothing really happened to the cart. It just, the detector started to see something in my barn here. I think it actually saw the floor. Ignore everything past this point. So look what happened when the fan was turned on and it was moving. So then you got steady motion. And look what happened to the velocity. It just continually increased in a nice, uniform fashion. Okay. See you next time. Okay. All right. So it really was, it was a similar kind of graph, but it was just very, very steady. So go ahead and sketch in the graph that we had.
With the fan attached, wouldn't it reach maximum speed and level off?
With the fan attached. Well, okay. So let's kind of think about this for just a second. We're assuming that we can ignore friction or wind resistance, right? So we're wind resistance. So there's no, we're assuming that we're in a magical world where there's no friction or wind resistance. So the only force that acts on it is coming from the fan. Is that okay, Julie?
Yeah, that makes more sense.
All right. So in that world, I know it's not the full thing. They're going to add in, more details as we go through these sections. But right now, it's just we're doing it kind of one force at a time to figure out what one force does, and then kind of layer it on top. So if you just have the fan blowing and everything else is ignorable, what would you say would happen?
Oh, the steady.
Yeah. Right. It would just right there's again, nothing's changing, so it's just going to keep on increasing. Yeah. So this is like that nice steady increase. Okay. All right. What do you guys think would happen if you could put many carts in a row, like back to back? Yeah. What do you think would happen if you could do, or not many carts, many tracks back to back, or in my case, if I just let this thing go for longer and longer distances then? Julie, can you use your last question to guess an answer here?
I was writing something, so I didn't hear your question.
Right. That's okay. So if I just let this thing travel farther and farther and kept the fan blowing just as it was, or turning just as it was, what do you think would happen to the speed?
It'd be infinite because there's no reaction to wind or friction or anything.
Right. Yeah. And so, insofar as I can ignore that, okay, so that would be a prediction.
But it cannot be infinite. There is a limit for the speed.
So it's all in the caveats. So we are assuming that we're ignoring friction, we're ignoring wind, and we're essentially assuming an infinite battery life, right? We're making various assumptions here. Now, you're right. All of these things are not true. And so that means eventually you'd have to deal with that. Eventually those would become significant and you would see the effects. But the idea would be here is we're trying to imagine a world, we're trying to figure out what happens with one force. And then we're going to extrapolate, even though we can't physically create those scenarios, we're going to extrapolate and figure out what happens with one force. And I agree. Reality says you can't really do that forever. I mean, I can't let the cart go forever. It runs into the barn door or something. All right. So I've got another video where we watch it go even farther. Maybe if I can figure out where I put it. Hello, I'm back with my partner Finn. Hi. And we're going to do a similar experiment as we did before, but this time we're going to allow the cart to go farther and farther and farther. So we have to scoot back, so we're not in the way. And we're going to see what happens to the graph as the force is just continually applied over a greater and greater distance. Okay, so Finn, can you get ready? And then when you hear the detector, turn it on. Okay. Hit the wall. All right, so let's, what I will do is auto scale. Okay. Thanks. So notice, okay, once it got way out here, it was hard to pick up. But notice, as long as there was one steady force applied, it just went faster and faster, faster, and without any sign of stopping. So that indicates that when you have a single force and it just is a steady force, it doesn't change. If you could apply it forever, the cart would go faster and faster and faster with no apparent limit. Interesting. All right, can you guys, are we all back? Is it showing? Okay, so Suleiman, so that's all in this idealized, this magical universe where there's no friction, no wind resistance, the battery can go forever, no matter what. Yeah. Have you guys, every once in a while you will hear things in the news about space travel, and they'll talk about trying to use light and lasers to make a spaceship travel. And the idea is, instead of using a fan to blow air, you basically shine a laser off the backside, go to outer space where there's very little wind resistance. I mean, almost essentially zero. You have a laser shining off the backside, and it turns out that there is a little bit of a recoil force. If you shine a flashlight, there's a tiny recoil force that pushes you in the opposite direction. In the classroom, I have my laser. I've got a little thing that spins around. You can make it spin because of the laser light. You can see the force it exerts. I'll show you. Anyways, their idea is basically, though, once you get up into outer space, you turn on lasers, and then the recoil force from the laser makes the spaceship go a little faster, a little faster, a little faster, a little faster, and a little faster and faster, and you speed up and go faster and faster and faster. And in each moment, the actual force coming from the laser light is tiny. But if you just apply it steadily over over years, then the spaceship will go, it gets going quite fast. If you wait 100 years, and we're talking about long-term space travel, if you want to go to other planets and things, then the ship gets going very fast in this kind of situation. So it's kind of like running that fan, being able to run that fan for 100 years with essentially no friction or wind resistance. The cart would go faster. It'd be going really fast after 100 years if you could let it go that long. Okay. All right. All right, their video is exactly the same as mine. All right. Let's go through some of these. Okay. So their video is just the same. The speed seems to just increase without limit. It seems to just the longer you let the fan blow, and the longer you let it move, the faster it seems to travel. Okay. So there you go. Let's kind of fill these in. What happens to the speed of an object while a single one force acting on it in the same direction as the motion, what happens to it? When you have one force that's pointed in the direction it's traveling, what happens to the motion? Yeah.
It's gonna speed up
Yeah.
by time.
The speed continually increases. Yep. What did I do? I don't know what I did there. I'll just write it with the stylus. Okay. And what experiments kind of showed us that? Well, we just did it. So, right, what were the experiments that we had? I pushed the cart with my finger. I also kind of pulled on it with the force probe. I kind of pulled on that. And then we had the fan. All of those gave the same result. So, finger, push, pull the force probe, and fan experiments. They all were consistent with that statement, that it will just increase in the direction of motion. Okay, let's go through these summarizing questions. If a cart is at rest and a single force acts on it, what happens? So if it's at rest and a single force acts on it, what happens to the cart? That'd be kind of like the soccer player example. So what happens when a force acted on the ball in the soccer story?
It's gonna speed up
Yeah.
in a short time and
Yeah.
gonna decrease.
Well, okay, but if there's just one force, we wouldn't have then you don't have the friction. So just the kick. Yeah.
It's gonna.
Yep. So the speed will increase. Speed will increase in direction of the force. It'd be kind of weird if it was the other way. If you pushed it and it started moving backwards, that'd be kind of weird. All right. In general, during the time a single.
Can you scroll down a little bit so I can finish writing?
Oh, sorry. I'm sorry. Yeah.
That's good. Thanks.
So when you push on it, the speed increases, and the way in the direction of the increase is in the direction of the push, because it started, starting at rest. All right. It says during the time a single force, again, one force, no friction, nothing, not just one thing, acts with a constant strength on an object in the same direction as the motion. So we're thinking about the fan, right? That's like the fan. What is the object's motion like? Does it move at a constant speed? Does it continually increase? Does the speed only increase at first and then become constant after a short time? And what activity, what evidence, what did we do? Well, I already gave you the last part. The evidence came from the fan. So what did it look like?
It's gonna speed up continuously. Its speed's gonna increase continuously.
Speed
And
increase.
evidence is the experiment that we did earlier with the fan.
Yep. Right? The speed will increase continuously. We know that because of the fan experiment. Yeah. All right, Julie, I want you to answer this one. Number 3. When you're trying to push your finger to the cart with a constant force, you noticed, or I noticed, I told you about it, that the cart was running away from you, it's getting away from you. Why do you think the cart behaved this way?
Because there was no opposing force to interact with it, so it just kept going and
Well,
going.
remember, this is the question you answered using energy ideas.
The kinetic energy continued to increase as our CPE decreased.
And why
But
wasn't I
because it
able,
was a fan, it'd be a kinetic energy, right?
yeah, and why wasn't I able to keep up?
Because you're old. No.
Oh, yeah. All right. Well, just remember the final.
Just kidding.
Yeah,
No,
the final.
we can
Okay.
only go so fast. So
Well, there is some truth to that, right? I mean, but you're able. So what happened was I was not able to deliver enough energy. There was just a physical limit to how much I could deliver. Yep. Yeah. Now, in my defense, it also was the fact that kind of got a little bit out of my arm's length. So it could just be my arm wasn't long enough. Probably that's what it was. Not that I'm old. Yeah. So, so I would say, increasing speed requires increase in kinetic energy, and there is a limit to how fast I can deliver energy. Or, as Julie said, old age. Yeah. All right. Suppose that while the cart was being pushed along the track by the fan unit, one of the fan blades jammed so that the fan unit immediately stopped pushing on the cart. So it's going along, the fan's spinning, and then it stops spinning all of a sudden. Or if you wanted to, you could imagine that, I don't know, a wire broke and it just stopped propelling. Okay? So the cart's, you turn it on, cart starts to move, and in the middle it just stops. But assume there's plenty of room, it doesn't hit the wall or anything. What do you think would happen to the cart? Can you sketch a speed versus time graph? That'd be an easy way to do it. What do you think would happen if fan unit just stopped working for some reason?
It's gonna go constantly in a constant speed, or is there a friction? If there is friction, then it's gonna decrease.
No friction today. It's a magical day.
Then it's gonna go in a constant speed.
So how would we draw? Can you sketch in? Can you draw in what you think the speed versus time graph would look like?
Yeah. So here in the 4.
In 4, yes.
Do I need to create a new graph there, or?
I think you can just annotate and just.
Oh.
Was it not letting you annotate?
In the 5th graph, there's speed versus here.
Like right here, yeah.
Well, if there is graph, it's gonna, like, while the fan is operating, it's gonna go increase continuously, and when fan is off, it's gonna go. My drawing is bad. Something like that.
We're laughing with you. Yeah. All right. Okay. I see what you mean. Let me kind of edit it here. Well,
Okay.
I can't really edit it, but I think how about this? Up, 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 and then the fan stops.
Yep.
Is that what you were shooting for?
Yes.
This is this would be speed versus time. Why is that? If you don't have the fan blowing, then you don't have any force. So why is there still speed?
Because we still like have speed, and if there is no friction or any force, because of the convention, energy convention theory,
Well, all right, hold on.
like energy cannot transfer to.
All right, well, let's
Oh.
phrase it with forces here. So do you need a force to have a speed?
No.
No, that's why it's okay.
Okay.
That's why, right? Forces cause changes in speed. They don't cause speed. So it's okay that you have a speed, even though there's no force. So we have, if we were going to sketch the force versus time graph, it would look like constant, 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 and then down to 0. Whoa. Like that. So it'd be constant force, no force, constant force, no force. And it's okay that there's no force, but there is a speed, because forces don't cause speed. Forces cause changes in speed. Is there anyone who's confused on that? It kind of, when I say it, it always sounds like it's kind of like I'm being tricky with wording or something. But it's really important to understand that forces don't cause speed, they cause changes in speed. That's really important to understand. Okay. All right. Beginning of this activity, you sketch a speed time graph, soccer player, quick kick, and then what's going on here? All right. Quick kick, and then slowed to a stop as it rolled across the grass. Sketch this graph again on the following page with any changes from the original you wish to make. Okay, so go ahead and sketch it as you think it would look like. I think we all had that one, so I'll go ahead and sketch it in there. That one looks something like that, and then whoa, all right, that, and then kind of a slow, steady decrease to 0. And then it says on the graph, use colored pencils to indicate the section or sections of the graph during which there was a constant contact, push-pull between the foot and the ball. Can somebody tell me, where would the foot and the ball be? I'll draw it in if you tell me. How do I know when the foot was kicking the ball?
When there is a change in the speed is increasing, there is contact.
Yeah, so when it was increasing, right? So I'll put that in green. Right, so that's the green one. And then it says section or sections of the graph when a force acted on the ball in the same direction of the motion. Well, I'll do that one in blue, but we already answered that in the last activity. The force from the foot is in the same direction as that. So what they want you to connect is the idea that the force being in the same direction as the motion is connected with the increase in speed, and then friction pointed the opposite direction. And notice what that means. That meant that the speed decreases. So anyways, we'll come back to that, and then I think it's the next activity. I can't remember off the top of my head. All right. Is everybody clear how I labeled these? When there was a contact push-pull between the foot and the ball, the foot is what makes it increase in speed, so that's here. And on the foot kicks it in the same direction as its motion. So those are the same intervals. It's the same segments. All right. And we have 2 students in a previous class were discussing what they thought would happen if they could join many tracks together. So imagine you know, many tracks, and we still have, it's still a magical world. No friction, no wind resistance. Okay. So let's read their responses. Han says, I think that as long as the fan keeps pushing on it, no matter how long the track is, the cart will keep speeding up. Samantha says, I agree that the cart will speed up for a while. I just don't believe it could keep speeding up forever. I think that at some point its speed will become constant. In a world where there's no friction and no wind resistance, let's type whose answer you like the best. Han or
Han.
Samantha? Yeah, I agree. Yeah. And why do we think that? Can someone explain why they think that's the case? That's okay. So everything we've seen is forces somehow cause change in speed. So if there's one constant force, then there's going to be a constant change in speed. It's just that simple. It just keeps increasing and increasing and increasing and increasing. All right. So this is going to be kind of one of the key ideas so far. Forces cause change in speed. Not speed, changes in speed. All right. Okay, the last little bit has a lot of reading. So I want you guys but do it because it tells you how to write the narrative with using force ideas. All right? So what I want you to do for this activity is to draw the diagram the way they read how they tell you to do it. Okay, remember we had energy ideas. Here's how an energy diagram looked. Over here is going to be a force diagram. Okay, energy diagrams, force diagrams, they're different, but they both describe the same situation, just different ways to represent it. And we had an energy kind of narrative and a force kind of narrative. So I want you to read that, and then what I want you to do is draw a force diagram and write a force narrative and upload that for your for activity 2. Okay, so upload that to Blackboard. All right. So I want you to do the summarizing questions for activity 1, and I want you to do that diagram and narrative using force ideas. Don't write. So when you do a force narrative, you don't use energy ideas. You don't say kinetic energy and potential energy. You don't say that stuff. It's all about forces, those concepts. Okay. All right.